Thanks, everyone. I want to talk a little bit about static analysis for Java today. And I'm calling my talk an opinionated overview. On the one hand, I'll go over some very basic concepts of static analysis that I'm sure everyone can agree on, but I'm also going to go into some experiences that we have when we did the GraalVM Native Image static analysis. And I'm sure there are some, especially people in the research community, who will not agree to everything that I'm saying, but I hope I have good arguments for all of my points. First, to set the stage, is like, what's static analysis, and especially how does it compare to dynamic analysis and dynamic profiling? Basically, when you have an application that's running, then there's a number of methods that can be run in your application. It's like you have lots of methods on the class path, but we all know not everything will be executed at runtime. And basically, when you do static analysis, you want to find out what can be reachable, which means static analysis is always over-approximating the number of reachable methods, because it's like it will always find more methods that will be executed. On the other hand, when you do dynamic profiling, unless you have a complete test suite that really exercises every path of the application, then all sorts of dynamic profiling will always under-approximate the number of reachable methods. So for this talk, we are always talking about the static analysis. So it's like we are over-approximating our application. And we want to do that, of course, as precise as possible. So we want to over-approximate as little as possible. So if we want to find out the call graph for our application, there are a couple of well-known techniques. The first and the easiest thing is a class hierarchy analysis. Basically, what you're doing is for every virtual call that you find in your application, you look at your whole class path, you find all possible classes that override this method, and you say like, oh, this virtual call site can call the method, and everything that's on the class path basically then is reachable. That's very fast to be done, because like, yeah, you just go over your application once. But it's also a little imprecise, and the next more precise analysis is then called rapid type analysis, which in it takes the class hierarchy analysis, but it adds one important optimization and says like, oh, I only need to look at classes where I already found some instantiation site before. So it's like I don't look at my whole class path. I only look at classes where I found already a new instance before, and that kind of makes the analysis already more precise. But it's still fast. It's still kind of, you can do it in linear time, because like you go over your application once. And then when you want to get more precise, then you're getting into the area of points to analysis, where you really propagate types around your whole application. Basically, you have allocation sites of objects. In the literature, that's usually called an abstract object. An abstract object is an allocation site of an object, and that allocation site has a precise type. And then you propagate this type around your whole program. There's like you have one global interprocedural type value flow graph where values flow around. And then from every allocation site, you propagate this type to all possible usages. And that's where things get more precise, but also much more complex, because in theory, it's actually cubic complexity. In practice, it's kind of quadratic complexity, because it's very intuitive. When you have more types and more variables, when your application grows, then it's quadratic, because it's like you have more types that can reach every possible variable. And in the easiest case, points to analysis is context insensitive, which basically means you look at every method exactly once. And then you can make that more precise by going towards context-sensitive analysis, where you can clone a method as often as you want. So it's like, oh, I have a method. For example, when you have a call site context, then it's like you clone each method for a 2 or 3 level deep context. And it's like then you have every method not only once, but arbitrarily often. And obviously, the more complex your context is, the slower your analysis gets. So it's like you cannot give a complexity bound anymore, because in theory, you kind of can clone every method for every possible path, which is clearly not really feasible. So context insensitive points to analysis is kind of usually considered a good kind of baseline for an analysis, because it's still kind of fast enough to be done, but precise enough. And I have some interesting numbers on that later on. So you have already kind of two dimensions. We have precision and we have the time that the analysis takes. Interestingly, there's also a third dimension, which is called soundness. And it sounds very strange at first, but it's like basically how wrong are my analysis results? And usually it's like you would start off like, of course, I'm doing a static analysis. It can never be wrong because I'm doing a static analysis. But in reality, what lots of people have realized, it's like, even a language like Java is pretty difficult to analyze. And it's like, if you just cheat a little bit and kind of not handle all concepts of Java in all possible scenarios, then it's like, oh, you can get much better precision with much better analysis time. But my analysis might be a little wrong. And what does a little wrong mean? Basically, you have instead of over-approximating your methods, you just miss a few, so you're under-approximating. And there's this nice manifesto that a couple of well-known researchers in the static analysis community wrote nearly 10 years ago. And it's like, they say it's like, oh, if you look at Java, it's basically impossible to do a sound analysis anyway, so why do we even pretend? And let's say our analysis is not sound, because we just call it soundy, and it's good enough. And for a couple of use cases, of course, that's really the case. It's like if you want to do bug finding, for example, it's like, yeah, as long as you find enough bugs, it doesn't matter if you find all. So it's like soundy is good. But the main problem of a soundy analysis is like, you never know how wrong the results are. Because it's obvious, it's like if you would know where your analysis is unsound and if you know which things you are missing, well, then you would just include these things and your analysis would be sound. Which means if you have such a soundy analysis, well, how sound are you? How unsound are you? And that's like when you look at the literature of points to analysis, there are lots of academic papers published, and of course, you want to get your paper published. And how do you get your paper published? It's like, well, I show such a great improvement of analysis precision. But if your analysis is not sound, then you never know. It's like, well, do I have just a soundy analysis where I'm just missing a few of my reachable methods? Or have I reached the point where I really have a completely unsound analysis now? Because obviously, I can make a very precise analysis that also runs very fast, that just says nothing in my application is reachable. And it's like, takes no time. It's 100% precise, but also not really, really useful. So it's like, how do you kind of make an analysis that is soundy and everything, but still not too unsound? And when we were working on the GraalVM analysis for GraalVM Native Image, we kind of started on the other side, because like we said, it's like, well, we want to do ahead of time compilation of Java, which means it's like if we are unsound, even in the slightest corner case, then actually we are miscompiling Java code. And it's like when you are starting out from the compilation angle, then it's like anything that's soundy or unsound is kind of a non-starter. So we started out with a completely sound analysis and kind of then tried to make that as precise as possible. So I guess my point here is like soundy and all of that is nice, but it's like in the end, you can only really rely on your analysis results when you have a completely sound analysis. And that's actually what we did for GraalVM Native Image. That has some interesting implications because, well, a question for the room, is Java a static language or a dynamic language? Both, exactly. I would actually say Java is a dynamic language. It's statically typed, but in the end, Java is very, very dynamic. It has dynamic class loading. It has method handles. It has even invoked dynamic bytecode by now. So Java is very dynamic. But you don't even need to go to the new fancy things like invoke dynamic. You can go back to the very basics, like the Java native interface, which basically has a method allocate me dynamically an object of any type that I given in without running any constructor. Like that has been in the Java native interface forever. And if you want to do a sound static analysis that kind of supports that, you already kind of defeat a lot of the precision improvements that people propose. It's like, oh, you're trying to propagate types around from an allocation site to all usages, but you have this one allocation site in the Java native interface that can produce you at any time, any type, without running any constructor, which basically means forget kind of propagating around information and distinguishing different allocation sites of the same type, because there's this one JNI allocation site anyway. And the same holds for loads and stores of fields, because like we are via JNI and of course via SunMISC unsafe or JDK internal unsafe, you can read and write fields by offset without kind of knowing the field you're writing statically. Which means when you do a sound static analysis for Java, you actually reduce the precision, and a context-sensitive analysis actually does not make much sense anymore, because even your context-insensitive analysis is already kind of taking all of this dynamic stuff into account, and there's nothing you can improve on. And there are lots of other things why Java is actually pretty difficult to analyze statically. One thing is the separation of the new instance to allocate an object and a constructor. Then, of course, you have all the get and set methods. So it's like you actually never really have get field and put field methods, bytecodes inside a method in a larger context. You have them in separate methods. So if you just look at methods individually, then it's like you lose all the precision. Object arrays are pretty bad, because it's like there's no type safety at all. You have the dynamic array store checks. Interfaces are very bad, because like interface types are not verified, which means actually you cannot rely when you say it's like, oh, I want to rely on interface information to make my static analysis more precise. No, sorry. It's like you need to use the static analysis to actually prove that you don't need a dynamic check for the interface at runtime. So when you look at the precision, so these are actually the numbers for Spring Pet Clinic when doing the analysis from GraalVM Native Image. And in our GraalVM implementation, we actually have a complete an implementation of a rapid type analysis, and we have a points-to analysis implementation, which can be configured for all sorts of context sensitivity. What I have in the slide here is numbers for a so-called 2-object, 1-heap context sensitivity, which in the literature was kind of found as the best context sensitivity for Java. An interesting takeaway from that slide is that is like analysis time really varies a lot. It's like, oh, for Spring Pet Clinic, you can analyze it in 50 seconds with a rapid type analysis, and it takes hours for a context-sensitive points-to analysis. But when you look at the precision, so the right 2 columns, then it's like there is kind of a certain precision that you can reach with a context-insensitive points-to analysis, but that's it. It doesn't matter how many hours you spend in addition. It's like the precision does not really increase in any meaningful sense when going from a context-insensitive to a context-sensitive points-to analysis. On the other hand, when you look at the precision, it's like the points-to analysis is still significantly more precise than the rapid type analysis. So there is really a big precision difference between a rapid type analysis and a points-to analysis. Both in the sense of reachable methods, so it's like how big is the call graph. So it's like more reachable methods means the call graph is bigger, but also in the number of type checks on polymorphic calls. For these things, lower, of course, is also better. Basically, it means how many type checks are not proven and how many type checks are remaining after the static analysis and how many polymorphic calls are remaining after the static analysis. So that means how many call sites did the static analysis not devirtualize to a direct call. So the takeaway from this slide is like points-to analysis is good, but context-sensitive analysis actually does not make much sense. But still, also the context-insensitive points-to analysis is significantly slower than the rapid type analysis because it needs to propagate all these types around. Now, of course, it's like we want to have the same precision as a points-to analysis, but with only the time necessary for the rapid type analysis. Because also what I did not, what you don't see in this single point is like, well, how does the analysis time actually grow when your application grows? And for the benchmarks that we have, it's like for rapid type analysis, you really see a very nice linear growth. So it's like if you double your application size, the analysis time doubles. But if you look at the points-to analysis time, then it's like, oh, you see this quadratic behavior, and for everything that's quadratic like that, at some point you reach an application size where your analysis is no longer feasible. Which is bad for GraalVM Native Image, because like when people give you a large application, at some point you say like, oh, sorry, analysis takes too long, I cannot ahead of time compile this application anymore. So what we came up with is actually a very simple idea, because the precision from that points-to analysis gives you actually comes from small typesets. It really matters if you have a variable that can have 1 type or 2 types or 5 types, because like based on that information you can optimize. It really does not matter at all if a variable can have 100 types or 1,000 types or 10,000 types, because it's like once you have reached 100, all optimization potential is gone. So it's like what we did is kind of a hybrid between the rapid type analysis and the points-to analysis. Basically do the points-to analysis, but if a typeset grows beyond a certain fixed threshold, then just fall back to the declared type information like rapid type information. And what you get then when you do that, it's like we call this that points-to analysis with saturation. And then your points-to analysis also scales linearly, because like you're no longer kind of propagating around these large type states. And the really good news is that in this points-to analysis with saturation, you still get most of the precision of the standard context insensitive analysis. So the number of reachable methods, type checks, polymorphic calls does not change much compared to the baseline. But the analysis time is now very close to the rapid type analysis. So the takeaway from that is like you can actually do a sound analysis for Java that scales kind of linearly and still gives you a reasonably good precision. What can the static analysis do for you? I have a pretty simple application here where I have my data class and I allocate an array list and then I set an element. So kind of very simple in the source code. But actually, Java is not that easy. When you look at what really gets executed here, is like you have a couple of implicit null checks. You have the implicit interface type check, because my field list has an interface type. So actually, before we invoke the set method, we need to check that this list is really an interface. Then you have sort of the implicit type check for the virtual dispatch of the set method. And then you also have the implicit array store check for the array list .set method. So what can the static analysis do? It's like it propagates around even in the context insensitive sound analysis. It propagates around the exact type of this list for this list field. It static analysis proves that is an array list. So it's like that means an interface type check is no longer necessary. The virtual dispatch is not necessary anymore. But even for the array list internal implementation, where it's like this element data array is a Java long object array. But what the static analysis proves, it's like that this array really is only a Java long object array. So it's never kind of a subclass of an object array. So also no array store check is necessary. So it's like even the pretty simple context insensitive analysis already kind of proves you and allows you to remove these 3 checks. I'll come back to the implicit null checks later on, because obviously we would like to remove those 2, because like we as developers obviously see that it's like, well, the list field is never null. So why do we still need a null check for that? And the same thing is like for the array list. We know that the element data field is never null. Why do we need a null check? But it's interesting to see, it's like the array store check for the element data array is much easier to remove than the null check. But before we come to the null check problem, let's give you some intuition why does a context-sensitive analysis really not work that well. And for that, we don't have to look much further than hash map. Because like when you look at the internal implementation of hash map, it's like, well, you have the hash map object, you have a node array, and then the actual node objects. And since many years, it's not even kind of a node array with real nodes. It's like hash map can also fall back to a tree map. So actually, it's a recursive data structure. A node can point to other nodes again. Which means if a static analysis, a context-sensitive analysis, wants to see through this hash map and tell you it's like, oh, the only thing that can come out of a get method is the thing that you put into via a put method, and really distinguish two different hash map allocation sites. It's like you need to look at this real-level heap context in a recursive data structure. And that's just too complex to really do in a static analysis in a timely fashion. So now the question is like, well, since the context-sensitive analysis doesn't really work, are we stuck with the current precision of the context-insensitive analysis? So it's like, is there anything else we can do? Obviously, there's always something we can do, and kind of we're able to increase the precision of the context-insensitive analysis quite a lot by actually, instead of improving the analysis, just improve the input of the analysis. It's like when you look at what optimizing compilers are doing, it's pretty obvious what they're doing. They're doing method inlining, they're doing escape analysis, they're doing constant folding. And it's like, yeah, you can do all of that after you do the static analysis, but you can do all of that stuff also before the static analysis. Because no one says that the input of the static analysis really needs to be the bytecode that comes from the class files, especially if you use your analysis results to kind of optimize code later on anyway. But also, if you just want to give people a software bill of material, it's like, you know later on the compiler is doing these optimizations anyway. So it's like if a compiler optimization later on removes some infeasible code path, then it's like you can do that also before the static analysis. But like for all of that stuff, it's like, yeah, just run your compiler optimizations before and make the life of the static analysis easier. For the problem with hash maps, there are also kind of very creative solutions. It's like, well, why have the static analysis kind of find out what's going on in the 7,000 lines of concurrent hash map? It's like hash map is a simple thing. You can only get out what you put in. And as long as you trust your hash map implementation and you have hopefully a correct hash map implementation, then that holds. And then just let the analysis use that information. And so it's like, yep, I'm not having the analysis analyze the hash map implementation. I just do a shortcut between the put and the get methods. And instead of making the analysis context sensitive, actually what helps is also to instead making the analysis a little bit more flow sensitive. I will come to that towards the end of the talk. But first look at the simple thing. What do we do when running compiler optimizations before the static analysis? And a very good use case for that is VarHandle, because as we all know, it's like, well, you can either store a field via normal put field bytecode, or you can store a field via a VarHandle. And when you look at then the bytecode that you get out, it's like, well, you have some VarHandle somewhere, you load it from a static field, and then you do an invoke virtual to set. And in that case, I use set volatile because, yeah, of course, when we use a VarHandle, we kind of want to use, for example, the different memory models that VarHandle offers, or we want to do a compare and swap on something. So it's like all the operations that a normal field access does not give you. And it's clear, it's like if you have a static analysis that really just operates on this untransformed bytecode, then the analysis cannot do anything with the VarHandle access anymore. It needs to either be unsound and says like, oh, I have a VarHandle access to this field, but I cannot analyze it, I completely ignore it. but then it's like, well, you use a VarHandle in your application and you get wrong static analysis results. Or you need to be conservative and say, like, oh, as soon as I have a VarHandle for a certain field, I need to treat it like any unsafe access, and it's like any field that is accessed by a VarHandle can kind of have any value and I lose all of the precision. Or you can do the thing with, you run compiler optimization phases, and it's like if you analyze your class initializer and you know it's like, oh, this VarHandle instance that's in my static final is a VarHandle for an instance field for my particular instance field here. And then you have the set volatile implementation, which now you have a constant VarHandle object. You can resolve all of that. You can inline through the whole VarHandle implementation. So it's like it's all the VarHandle method handle logic. But in the end, you end up in unsafe method that really does the actual field store. And the field offset you're writing to is also a constant coming from this VarHandle. And now you have an unsafe store, but with a known offset, and you can kind of combine it again to a normal field load. So when you look at what the GraalVM static analysis is giving you for these two use cases, it's exactly the same compiler graph, so exactly the same input for the static analysis. The only difference is like, yeah, you have on the right-hand side a store field node that has a different memory order set, because it's like, yeah, in that case, it's a volatile store, but the static analysis, of course, doesn't care about volatile versus non-volatile stores anyway. So by kind of doing constant propagation and inlining through the whole VarHandle implementation, actually the static analysis is now exactly as precise when you use a VarHandle as when you use a normal field store. And to come back to the problem, it's like, well, how do we prove that fields are never null? In Java, unfortunately, we have the separation between the new instance bytecode and the constructor invocation. And this means you would need a very complicated analysis to actually prove that an object does not escape, for example, to another thread before a constructor is completely finished. So even for final fields that you know that are initialized in the constructor, you can never be sure that the constructor has really been completely executed before some other load kind of sees the field. So it's like you would need a very expensive flow-sensitive analysis that kind of really distinguishes a bit the order in which things happen. And static analysis is usually pretty bad in kind of ordering things. But it's like we can do a few simple transformations to the input of our static analysis to kind of make the static analysis's life easier. Because if we look at what's going on in the original bytecode, it's like, yeah, we have allocation of our holder class. So it's like it's the same example that I had before. And you have the allocation and the constructor invocation in my holder constructor again. Then do the field store, but it's like the field store of the list field is kind of storing into the parameter, so into the object that already comes in. And the same, the array list constructor is like always storing kind of a non-null holder array, a marker value into the element data field. But it's like from the static analysis point of view, when you just look at the one method, it's like, well, it's a field store into an object that's passed in as a parameter. But what we can do now is we can do outlining of factory methods. It's a pretty simple transformation. We take an allocation and we take the constructor invocation and we kind of put these two things together into a separate factory method. So we increase the number of methods that we have. Then we do method inlining. So we inline the whole constructors into the factory methods. And then we run escape analysis. Actually, we run the partial escape analysis of the Graal compiler. What you get then is like, in my allocation now has the allocation of the holder class is just the invocation of the factory method. They have this funky name because it's like we need to make a unique name, and that's by adding a suffix to the factory method, so ignore that. But it's like in this factory method for holder, it's like, yeah, you invoke the factory method for array list, And then you have the allocation, which the partial escape analysis actually pushed down all the way to the end of the factory method. And since it pushed down the allocation, it already now kind of does the allocation of a new object and the initialization kind of as one atomic thing from the point of view of the static analysis. And the same in our factory method for the array list constructor. Or for the array list, it's like we have one atomic allocation and initialization of the array list. So it's like we have now, already before we run the static analysis, an input to the static analysis where it's clear that the field can never be null because the allocation and the field initialization is atomic from the point of view of the analysis. And now by just doing this simple transformation before running the static analysis, we can now also kind of prove that the no null checks are necessary in our little example here. So the takeaway here is like we can run pretty complex optimization phases to transform the input to the analysis, but it really pays off because it's like now the analysis can prove that we do not need null checks for a good number of field accesses. And it's clear here that it's like we are not increasing analysis time because like instead of having the three original methods on the top, now you have the three new transformed methods at the bottom. So it's like the input to the analysis is not more complex. So the analysis does not take any more time. To have a little bit more detail on the second point, how to improve precision, is like the special handling for collections is actually a pretty well-researched topic by now. We had an intern years ago kind of doing an approach called semantic models. So it's like, don't want to discourage you from reading our paper, but it's like actually the second paper published a few years ago is a even better approach. They call that shortcut approach, which really basically means it's like instead of having a static analysis that kind of tries to figure out what's going on in the hash map class, it really kind of in this value flow graph of the static analysis really puts in shortcut edges and is like, oh, instead of that my get method kind of can have all the values that come out of the hash map.get method and that kind of reads things from nodes from the node array. It really says it like, well, insert shortcut edges into the static analysis from the put methods to the get methods. And it's like, it's that easy. The get method can only return you what you put in. And as long as you trust your hash map implementation, then you get a more precise analysis. It's like, and in this paper, they actually show that with that approach, they actually get a pretty fast context insensitive analysis, but that's kind of more precise actually than the context sensitive analysis that they compared with. And the last thing I quickly want to mention is like, one thing that traditionally points to analysis is doing is like it's only tracking object values and not primitive values, because like, yeah, I want to find out what types my object variables can have. But ignoring primitive values is actually not really good, because like when you look at real world code, and my little example here is taken from the JDK virtual thread implementation, is like, yeah, there's an isVirtual method on Java lang thread, and it's a pretty simple implementation. It's just doing this instance of base virtual thread. But the static analysis can now prove that it's like, oh, if my application does not use virtual threads, the static analysis can prove that this instance of kind of is always false. But then, since the static analysis doesn't do anything with primitive values, it cannot propagate this simple effect to the caller, to my onExit method. And even though it's obvious for us that the body of this if block kind of is unreachable, because my application does not use virtual threads, the analysis is not able to prove that because there is this gap of the primitive values. But it's actually completely unnecessary to stop the analysis at primitive values. The same way you can propagate around types, you can also propagate around primitive values. You could do that in a very fancy way, propagating around ranges that primitive values can have. But it's not even necessary, because in the end, you only need to track around primitive constants. Also very intuitive. You just need to track around if something is 0, false, or if it's 1 or true. And you already kind of have most of the precision that you can gain. So it's like you don't need to make your analysis slower and much more complex. You just propagate around these basic primitive values. And then once you have primitive values, then actually it's pretty easy to extend it also to really track predicates. By predicates, I mean really only commit, you could say, the body of an if block once you have proven that the condition of the if is actually fulfillable. So instead of saying that, oh, this variable display that I have here is like it can have a value coming in as a method parameter, but it can also have this new frame display that I allocate in here. By the way, this example is taken from the Da Capo Sunflow benchmark. But in the end, the analysis proves that it's like, oh, the method parameter display of this random method is never null, which means the analysis proves that the body of this if block is never reachable. But by the time it has proven that, the normal context insensitive analysis has already kind of polluted your type flow graph with this new frame display graph that a type that it propagated down to all usages. And that's, in this benchmark, is kind of the only place where kind of the whole AWT implementation gets reachable in this benchmark. So it's like if you kind of cut out this one line, the number of reachable methods goes down to about half, because like it cuts out the whole AWT and Swing implementation and proves that it's no longer reachable. And so what we did is like, well, we say it's like our points to analysis now tracks predicates, and it means it's like only after we actually saw that this display value can be actually null, only then we kind of go into the if block and process that. And since in our case the display variable can never is always non-null, actually we never commit this new type. So what we have now, it's like when you translate that from static analysis terminology to compiler terminology, we now have a complete application global sparse conditional constant propagation, where kind of conditions are only kind of looked at when their predicates are really and their conditions are really fulfillable. So in summary, Java is statically typed, but otherwise it's a very dynamic language. And a point I try to make is like, if you ignore the dynamic aspects and say it's like, oh, my analysis is unsound and kind of ignoring certain aspects, then you might be in trouble, because you never know really how unsound your soundy analysis is. Instead, what we have in the GraalVM points to analysis is like we have a completely sound analysis. Of course, we don't have a proof that it's sound, but it's like, since we're using all the static analysis results for code optimization, it's like if something would be unsound, we would have already crashed in the last years of testing. But the analysis is sound, but it's still fast and scalable because of the saturation. But it's also precise because we're running compiler optimization phases before the analysis. And yeah, it's also open source. So it's like if you have a need to use a points to analysis in your project, then of course, I would recommend that you use our analysis, because yeah, it's sound, it's fast, scalable, and it's precise. With that, that's all that I had to tell you. Are there any questions or comments? Ron?
Yeah, so I was wondering, how do you handle JNI then in a sound way?
How do we handle JNI and reflection in a sound way? It's like, yeah, I did not tell you all the nasty details here. It's like you need some configuration as input to the static analysis. So you need to kind of list all the types and all the fields that you can access via JNI, because it's like, So it's like you need a configuration.
So, and you need to trust it.
Yeah, and you need to trust it.
One of the things we found is that reflection particularly can make the space huge. So because the moment you find anything, you register anything for reflection, anything that comes from there becomes part of the universe or part of the analysis. So you have to be very mindful.
Yes, everything that's accessible via reflection, you need to tell the static analysis ahead of time. Unless it's kind of like I had with the VarHandle example, if it's kind of reflective usage that kind of can be resolved automatically before running the analysis. So it's like if you have a class for name or with a constant class name, which actually happens quite frequently when people do a JDK or library version agnostic code. Is like, oh, I have a class that's not there in all versions, so it's like I do a class for name with a literal, and either the lookup succeeds or fails. And the same is like if you do a class.getDeclared method with a constant method name and a constant parameter list, because as we all know, it's like we always want to invoke private methods that we are not allowed to do directly. So it's like we use reflection for that. All of these things kind of are resolved automatically without configuration files before the static analysis. Okay, if there are no more questions, then thank you.